Okay, hi everyone. My name is Nikita Zemlevskiy, and today I'll be telling you about our work where we used IBM's quantum computers to simulate particle collisions. So I want to start off by giving some background about why we care about doing these simulations. So things are colliding all around us, even right now. So here on the right, I have two kind of physics textbook examples of collisions, one of the break shot of the game of pool, and another of a gas of particles in a box flying around and hitting each other. So for the most part, we know how to deal with these kind of collisions. We know, in this pool example, you can solve some kinematic equations and figure out what are the positions and the velocities of all the balls on the table after this collision takes place. And in general, when things are colliding at pretty low energies, we have good classical methods to figure out what are the dynamics of these collisions and what happens after the collisions take place. But when you go to higher energies, so when things are colliding at very high energies, like at these colliders, like Enrique was saying, for example, at the LHC, things get very complicated. So here I have a very similar picture to what Enrique was saying in the showing in the previous talk. And this is a kind of collection of many, many collisions, and these yellow lines that you see in the middle are the outputs of two particles colliding very fast. So as you can see, this is a very complicated event. Many different things can happen, and it's kind of the purpose of these colliders to record all of these events, record their probabilities, and try to learn about the laws of nature from these collisions. But like I said, it's very complicated to do with classical methods alone. That's why we need to build these experiments. So here I have kind of a cartoon of what goes on in these collisions. So you start out with two particles that are traveling very fast towards each other. Here I'm kind of representing them as these red and blue clusters. Maybe these are some kind of heavy ions like lead. And behind them I have drawn these envelopes, which I'm going to call the wave packet. And you can think of this as the probability of finding the particle at that given location in space. So yeah, these particles are traveling very fast towards each other, and eventually they collide, and a bunch of products come out. And it's the goal of the LHC to figure out what these products are and measure what happens. So like I said, it's very complicated to simulate the dynamics and figure out what the products of these collisions are with classical methods, but we believe that if we have a very efficient quantum computer, if we have a sufficiently powerful quantum computer, we can do this with quantum methods. And I just want to point out that if you're not directly interested in simulating scattering events, these kind of simulations are BQP complete. So what this means basically is that if you're interested in some other problem that is known to be efficient with quantum methods, in principle you could solve it by solving one of these scattering simulations. And so I'm not suggesting that you do factoring by simulating scattering, but in principle this is something that you can do. So now I want to give a little bit more background about some of the scattering simulations that have already been done to date. So here I have two examples, one in the Turing model and one in the scalar field theory. The details are not too important, but what is going on in these diagrams is that the time starts at the bottom and goes up. And at the beginning, you have these bright spots. These are the initial particles, the wave packets. And as time goes on, they move towards each other. They overlap, collide, and then they separate out. And what I want to point out about these simulations that have been done to date is that they've been mainly limited to low energies, so mainly where classical methods are good, and also limited to small wave packet sizes. And the reason you might want larger wave packets is due to the uncertainty principle. So if you think back about what the uncertainty principle tells you, it says that if you want to know what is the momentum of your particle with very high precision, then you won't have a lot of information about its position. And so what that means is that if you want a particle that's going with a very precise momentum, it's going to have to take up, its wave packet is going to have to take up a lot of space. And so in other words, kind of one of the bottlenecks so far for simulating these high energy collisions has been the size of the states that we're able to prepare. So here I'm showing two more examples of of now high energy collisions. These are classical simulations with matrix product states, and this is a very efficient classical technique in one dimension. So here I have two examples, one in the Ising model and one in the U1 theory. And again, the details aren't too important, but what you can take from these plots is, as you look at them from left to right, the energy of the initial collision is, the energy of the initial states is increasing, and you can see that some qualitatively different behavior is happening as a function of the energy. So on the left, these particles are basically just passing through each other and not interacting. In the middle, it looks like there is some bound state or some kind of particle at rest that's being created, and on the right, there are some really new particles created, and they're flying away. And you can tell that by looking at these new tracks that are closer to the center. And so I'll be showing a few more of these pictures later on. But what's nice about these kind of simulations is that they're very visual, and just by looking at them, you can tell what's going on as a function of time in your process, what kind of states are being populated, what particles are created, et cetera. So this is kind of a nice motivation to run these simulations on a quantum computer where classical methods might not be as readily available. So like I said, one of the bottlenecks for doing these high energy simulations in the past was the state preparation requirements. So in the past, before our work, most of the state preparation methods to prepare these wave packets required either a circuit depth that was at least linear in the size of your wave packet, or otherwise they would require an exponential classical computing overhead to figure out what are the circuits to prepare the state you want. And while maybe linear in the size of the state is formally efficient, this kind of precludes any near-term demonstrations. And so our method that we developed and that I'll tell you about in this work, actually the depth does not depend at all on the size of the state that you want to prepare. And it also doesn't depend on the dimension, so if you wanted to do scattering in 2D, you can still prepare your states in the same depth that I'm about to show. So this is a really nice reduction in resources that you need. So I want to say that we have tested this method in a variety of theories. So this is not just specific to what I'm about to say, but for the sake of concreteness, I'll just focus on the one-dimensional Ising model. So this is a familiar Hamiltonian that several people in the conference have already showed, so I'm not going to explain how it works, but this is a fairly standard spin model. And we work with these values of the x and z fields such that we have two stable particles. And what I mean by stable particle is that the kinematics of this model do not allow these two particles to decay into anything else of lower energy. And so, yeah, we have two stable particles. The lightest one I'm going to label by this blue ball, and the heavier one I'm going to label by this red ball, and I'll use this notation in the next slides. So I want to motivate the state preparation algorithm by looking at what is the structure of the Hamiltonian of a theory like this. So if your theory has translational invariance, by which I mean if you pick up the theory and move it by one site, nothing changes. So if you have translational invariance in your theory, you can write your Hamiltonian in this block diagonal form, where each block is labeled by the momentum of that block, k. So if you look at the k equals 0 block, the ground state of that block is the vacuum of the theory, so the absolute ground state of the whole system. And if you look at the k not equal to 0 blocks, the ground state of those blocks are single particle eigenstates. These are plane waves. These are states with definite momentum k. And what we're really after is some kind of localized single particle state, a wave packet. So here I have an example of a wave packet in a Gaussian wave packet. This is just a superposition of these plane wave states psi k. And so I'm going to explain our algorithm to prepare these kind of states. So as a warm-up for preparing these wave packet states, first let's talk about preparing one of these plane wave states psi k. And you can do this in two steps. First, you prepare some state that is in the correct momentum block, hk. And one easy state to do is this state that I'm calling k, which is the state with all zeros and a single one, and the superposition of that with all states related to it by translation, weighted by the appropriate phase, such that it is a state of definite momentum k. So this momentum is in the correct, this state is in the correct momentum block hk, but in general, it might have contributions from higher energies. It's not a single particle state. It might have contributions from multiple particle states. So after that, what you do is you minimize the energy of this state with some circuits that don't change the momentum of your state. So this is a translationally invariant circuit. And you do this with some variational techniques. And once you do that, you get to the ground state of this momentum block, and that is this plane wave state that you're after in this case. And it turns out that you can just use linearity to, you can just use this process, you can just use linearity to apply this process to also prepare wave packets. So like I said, you can do the same thing to prepare these wave packets, but here instead what you do is you start with this W of k state, which is just the superposition of these momentum states k that I was showing on the previous slide. And what I want to point out about these W of k states is that if you set all the coefficients to be equal in this W of k state, then you get this familiar W state that people have studied a lot in the context of quantum cryptography and networking and so on. And so as a result of that, people have thought very hard about how to prepare these states efficiently. And so here I'm showing several references that we use. So we extend the methods of these three papers and kind of generalize them. And we use these dynamic circuits, so non-unitary operations, to prepare this W of k state in a fixed depth of 7. And this doesn't depend on the size of the W state. It doesn't depend on the kind of coefficients that you choose. It doesn't depend on the momentum. It just works. So this is a really nice simplification and reduction in resources. So once we have this W of k state, again, we minimize the energy with circuits that do not change the momentum content of your state. And what this does is that for each contribution to this W of k state, it goes to its respective ground state in that momentum block. So this really prepares the wave packets that we're interested in. And so what this plot is showing you is that as you add more and more steps to this variational energy minimization circuit, the energy decreases, but so does the infidelity with your target state. So this is just saying that the energy minimization technique also improves the overlap with the state that you're really after. So this really works. And so at the end of the day, what we're really after is circuits to run on quantum computers, and oftentimes, in our case, we're interested in running circuits that are larger than you can do with brute force classical calculations. So in this case, we can take advantage of the fact that we're working in one dimension and use matrix product states to train these circuits directly on the system size that we're interested in. And for this, we use the MPS package QIMB. So here, again, I'm showing some pictures of MPS simulations. This is results of using this algorithm that I just explained to you to prepare these wave packet states and then simulate the scattering process. So what's going on here is that I'm starting with 2 blue particles, so 2 light particles, and if I give them enough energy, there is some non-zero probability to produce a red particle from these 2 initial blue particles. So here I've labeled this total energy divided by the threshold energy, and what this basically means is that if you're at this threshold, you have some non-zero probability to do this particle production. And the way that you can see that really these red particles are being produced is that you can see this faint green track that's closer to the center of the collision. And the reason that means that there is a red particle there is that these red particles are heavier, so they travel slower after the collision. So that's why they're closer to the center of the lattice. And I'm going to use these labels a few times throughout the talk to separate these 2 cases. So the left case I'm going to call inelastic scattering. This is when the particles just pass through each other. The left case I'm going to call elastic scattering. This is where the 2 particles are just passing through each other. And the right case, where I have 2 blue particles and end up with 1 red and 1 blue, I'm going to call inelastic scattering. This is when you have particle production. So just so we're all on the same page, I have a movie. This is basically time slices of the picture on the previous slide. So you start out with 2 wave packets at the beginning, then around time equals 8, they fully overlap and collide, and then later on they move away from each other. And around time equals 30, you can see these extra bumps separating out from the main peaks that are traveling away. And these extra bumps are these tracks of the red particle, the heavier particles separating out. And it's going to be the goal of our quantum simulations to see these bumps in the results of the quantum data. This is what we call particle production. So now I'm going to switch the gear a little bit and tell you about some of the tricks that we use to actually get results from the quantum computers that we have today. So one of the nice things about running on quantum hardware is that sometimes you see things that you don't expect, and you have to do work to figure out what's going on and that kind of dissect the problem. And for us, one of the things that happened was about errors. So once we were starting to run these simulations, we realized that the results were a lot noisier than for simulations of similar depth that we have run in the past. And we understood that because now our wave packets, our initial states are much larger, they have to travel a longer distance to fully overlap, scatter, and separate away. And what that means is that we have to simulate the system for a longer amount of time, even if the circuit depth is the same. So what I have shown here is a cartoon of 2 circuits whose depth is the same, but the circuit on the right evolves the system for double the amount of time than the circuit on the left. So the Trotter step is twice as big on the right compared to the left circuit. And suppose that you have some error that takes place at the beginning. If you evolve the system for twice the amount of time, the error can contaminate proportionally more measurements that you do at the end. And so what this told us is that the error is really spread with the simulation light cone and not with the circuit light cone. And this really made us be extra picky with the qubits and the gates that we use on the device to kind of avoid this situation where, because we're evolving for such a long amount of time, errors that might happen very early on are going to contaminate a large portion of your device. So as with any quantum simulation today, we have to do error mitigation to get anything meaningful out. And the main ingredient in our error mitigation strategy is to run a second set of circuits whose answer we know ahead of time, either through some classical means or using physics intuition. And these additional circuits have to have the property that the noise profile of them has to be similar to the circuits that you actually care about. And then you use this to learn about the noise and adjust for its effects. And in our case, we use the time evolution of the ground state of the whole system. And this is easy classically because the ground state is an eigenstate of the Hamiltonian, and it does not evolve. And any errors that any evolution that we do observe, we attribute this to noise in the system. And so we use this to learn what kind of noise processes are going on and account for its effects. And here I am kind of sweeping under the rug a lot of other tricks that we use to make this work. And if you're interested in learning about them, please come talk to me after the talk. So here I'm just showing some of the results of applying these error mitigation techniques, and there's kind of a lot of things plotted on this slide, so let's just focus on this panel at the bottom. Here I have several sets of data points. These data in the middle is what are the raw results that come out of the quantum device. And then these points, these circles on the bottom are the results after error mitigation. And I'm comparing that to the results from matrix product state simulations. This is these dashed lines. And this is the kind of classical expectation that we want to reproduce with quantum computers right now. And I'm also comparing it to the results that you would get if the quantum computer was giving you completely random answers. So this is the pure noise. And what you can see, if you squint a little bit, you can notice that there's this line break here. And what this means is that these raw results from the quantum device are much more similar to the pure noise values than to what you expect that it should get. But after applying all these error mitigation techniques, you see that you really reproduce these classical expectations quite well. So now I'm going to show you some results from other time steps from the quantum computer. So on the left, I have the same plot of the matrix product state simulations that I've been showing to you before. And here I've selected several time slices for which I'm showing data from the IBM quantum computer, IBM Marrakesh. So what's going on just to say it again, what's going on in these plots is that at the beginning, I'm starting with two particles that are traveling towards each other. That is this plot in the bottom. Around T1 equals 8, they are fully overlapping. And after that, they are traveling away from each other. And here are the gates and the qubits that we used on the quantum device to run these simulations. So these are simulations from 104 qubit lattice. And so what you can see from these results is that initially the agreement with MPS is quite good. And however, as you go out further in time, the circuit depth does increase. And as a result of that, there are some systematic errors that we see. And yeah, so the deepest circuits that we ran for this simulation were 130, and they had 5,500 2-qubit gates. So originally, I was telling you all that the goal of our quantum simulations was going to be to see these bumps of the heavier particles separating out from the lighter particles. So that would be around here. And you would see that if you kind of go out a little bit further in time than we were able to on the quantum device. And so unfortunately, because of the effects of noise, we were not able to actually see these bumps. But what we were able to see is evidence that these heavier particles are produced and they do exist. And the way you can see that is by looking at the region of one of these bumps, for example, at T3. Because the red particles are heavier, they are traveling slower, and so they contribute to this energy density in a skewed way. They are located closer to the center. And so if these red particles exist, then this energy distribution should be skewed closer to the center. And this is actually a good indicator of whether you have inelastic scattering, whether you have particle production or not. So in this plot, I have two lines. The blue one is for when you do have particle production, and the orange one is when you don't. And so I'm plotting this skewness metric that we have come up with. And what this is telling you is that you can really use this to separate out between elastic and inelastic scattering. And this is what we see in the quantum data. So here on the left, I am comparing one of these bumps, the state after the collision has taken place. I'm comparing its skewness to the simulation where I just have one particle propagating without any interactions. And what you can see is that there is a significant difference in the skewness despite all of the noise and approximations that we make. So this gives us confidence that while we have not seen explicitly these red particle bumps, we believe that they really are there. So yeah, with that, I hope I have convinced you that even with these early quantum simulations, you can still see meaningful results of these scattering simulations. And if quantum simulations had a roadmap, I would kind of give a half check to scattering in 1D at this point. But yeah, I want to say thank you all for listening. Thank you to my collaborators, Roland, Mark, and John, for their contributions to this work. And of course, thank you to IBM for giving support and time for running on their devices. Without them, it would not be possible. Thank you.